I'm going to present our paper titled CLIPPO, Image and Language Understanding from Pixels Only. In this paper, we propose a novel vision language model similar to CLIP, which uses a single vision transformer backbone to process visual input, text, and both together, all rendered as RGB images. To train this model, we use a simple CLIP-style contrastive loss. This setup simplifies input pipeline and transfer procedures and also sidesteps tokenizer design, which can be tedious, in particular in heavily multilingual setups. CLIPPO, that's how we call our model, matches performance of an equivalent contrastive model with tokenizer in zero-shot image classification, image text retrieval, and visual question answering, and it also outperforms prior pixel-based language modeling work on the GLUE benchmark. Let's dive into more detail. So first, we use a character lookup-based unifont renderer, which is fast and efficient and doesn't slow down our input pipeline. We use font size 16 for the rendering, and this corresponds to the patch size of the vision transformer models we use. We mainly consider two baselines. Our reimplementation of CLIP, which we call CLIP star to avoid confusion with the models released by the original CLIP paper, and 1T CLIP or single tower CLIP, which is a single tower model with separate embeddings for images and tokenized text. So this model actually uses a externally trained tokenizer, but also has just one backbone like CLIPPO. In terms of training recipe, we develop a recipe that works well for CLIP, and we just use it for CLIPPO and 1T CLIP without any modifications. To train our model, we use the Webley dataset, which contains 10 billion images with all text in 109 languages. We use the English subset of Webley for most of our experiments, and when we evaluate our models on multilingual vision language tasks, we use the full Webley dataset for training. Optionally, we also co-train our model with text pairs, specifically consecutive sentences, sampled from C4. Let's dive into the results. I will start with the vision language results, more specifically zero-shot and three-shot classification and retrieval. In the first three rows of this table, you can see a comparison of our reimplementation of CLIP, 1T CLIP, and CLIPPO. It can be seen that CLIP achieves the best performance, but this is not surprising given if it has twice the parameters of CLIPPO. 1T CLIP and CLIPPO achieve similar performance, and as we add C4 data to the training batches in CLIPPO, we can see that the performance gets slightly worse. However, this is not surprising given the batches now contain fewer vision language pairs, and therefore we have a weaker training signal. Also, we will see later that in exchange, the CLIPPO models will have stronger language modeling performance. And as usual, if we scale up the models, we get improvements across the board. Let me move on to multilingual vision language results. Here we consider multilingual zero-shot retrieval. We use the cross-model 3600 dataset, which contains diverse images, each annotated with captions in 36 languages. And we compare against the one-tower CLIP, and both CLIPPO and one-tower CLIP are trained on multilingual Webley. It can be seen that for a T5 tokenizer or a tokenizer that is trained on the alt text of the Webley dataset, CLIPPO outperforms one-tower CLIP, and one-tower CLIP only outperforms CLIPPO if it can rely on a tokenizer that has been trained on a large multilingual corpus. So this means that that model, that 1T model, relies on a lot of external data which CLIPPO doesn't have access to. Next up are visual question answering results. So here we use a very simple approach to transfer the CLIPPO models to VQA. Specifically, we simply render the question at the top of each image, and we train or fine-tune the CLIPPO model to classify the most likely answer from the training set. We also apply this procedure to a few baselines, including the CLIP vision backbone, 1T clip, and a supervised pre-trained model. Here we can clearly see that CLIPPO outperforms other vision backbones, fine-tuned in the same way, and it achieves performance comparable with strong baseline VQA models that rely on CLIP as a vision backbone. If we increase the resolution, our models are even competitive with dedicated VQA models, which are trained with a complex loss and dataset mix on external VQA data. Note that our models are only fine-tuned on VQA v2. Finally, let me present the language results on the GLUE benchmark. Here we can see that the 1T clip text encoder and the CLIPPO text encoder are competitive with BiLSTM style language models, and the CLIP text tower text encoder is outperformed by these 1-tower models. If we add text pairs to the CLIPPO training mix, we can see that when half of the mini batches consists text-only data, we match the performance of the prior pixel-based state-of-the-art language model, namely Pixel. And if we train on C4 data only, we outperform it by a solid margin. In conclusion, CLIPPO shows that pixels alone are sufficient for multimodal vision and language learning, using only image-level contrastive loss. So no word-level loss, no masked language modeling loss, just a simple contrastive loss. In the paper, we present many more results, and in particular, analysis of the CLIPPO representations. We also provide code, pre-trained models, and a collab